Welcome back to After Hours Engineering. In the previous episode, we learned how to simulate a sequencer by manually manipulating the control signals ourselves. In this episode, we take the next step and build a simple melee FSM to do the manual work for us, because we're lazy like that. We'll need a test bench that not only drives the FSM, but generates the clock and a reset signal for us. And finally, we'll stop just short of synthesis and perform only the build and route so that we can learn about the inference of latches. Let's do it. We'll start by comparing our melee module against a melee FSM diagram up here. As you can see, we have our usual parameters, we have our inputs defined, and all of the outputs. On our FSM, we're going to have quite a bit of outputs, and this is just a simple example. We have our usual local parameters. In this case, we're defining the 4 states of our FSM. We have some internal variables, vector states, and we have all of our data path control signal registers. Then for the simulation, we have an initialize to state vector 1. Now if we look at this portion of the diagram, you'll notice that I have this always vector state. That corresponds to the diagram over here where it says combinatorial output logic. And you'll notice that we have another always behavioral block right here, and that corresponds to the memory and the next state logic. If I pop each one of these open, you'll see what they look like. The vector state is going to be the largest of the two because it's trying to track the movement of each sequence as we move through. And in the second portion of this episode, we're going to take a look at what's called latch inference. And I'm going to be demonstrating by removing one of these initializations here, or default settings, in the always block. And as you can see, we have a case statement. And in each particular state, we go ahead and set our control signals to different values throughout them. And then we move to the next state. And again, down here, we reset some values and move to the next state. Plus, we have a default state that should never actually be reached. Now, that takes care of the combinational always behavioral block. Let's take a look at the clocked or the synchronous side. You can see it's pretty small. At the positive edge of the clock, any positive edge, if the reset is active, then we set back to vector 1. Otherwise, we actually move to whatever the next vector has been set to. That's it for this section of the melee diagram. And then finally, we take all of our internal control signals and route them to the output. That's the melee FSM in Verilog as a module. Here's the test bench that's going to drive that melee FSM module. As a reminder, in the upper right, we have our goal, which is to move the reset vector FF over to the memory address register. So as usual with most of our modules, we have our local parameters, we have wires to accept some of the outputs, our usual inputs, and we have a master reset for our melee FSM. We also have wires in between our modules, and here is our first one, the MUX PC. The program counter, should be identical because we used this test bench prior. Then we have our MUX address and our memory address register. And then finally, here is the actual melee FSM that we're going to test. This is the device under test. We have our usual things, the clock input, the reset, which is driven by that matrix reset, the outputs, and then finally we have our clock that we'll be synchronizing our FSM to. We have our usual dumping, we have an initial reset vector, we wait 3 cycles for the reset, which is active, and then we deactivate it. Then we run more cycles to actually cause the finite state machine to move through its set of sequences, and then finally we're done. Now that we have our test bench and our melee state machine module, we're ready to run the simulation. I've done that, so let's bring it up. We know that in our state machine, the very first state is vector 1, and in that state we do 2 resets, the program counter and the address register. And as you can see, the outputs go to 0 on both the registers. In the next state, we adjust the PC source and the PC load. So we're switching on the source from 0 to 1, 0, and we're dropping the load low. And we know that on the negative edge, where all of our action takes place, things change. And sure enough, that constant value that was on the input of the mux is now on the output of the mux. This is great. We now move to vector 3. And in that state, we bring the address register, we set the address source and the memory load, and on the negative edge of the clock, we take action. And sure enough, finally, the output of the address register contains what we started off with, which was the reset vector. So our state machine appears to be working. And as you can see up here, the next state is vector 4, which really doesn't do anything. And then finally, we wait 1 clock cycle, and our test bench comes along and resets the state machine for 3 clock cycles. And as you expect, our outputs, whatever they were, in this case they were FF, goes to 0, and our address register goes to 0. So based on this timing diagram here, it looks like we've successfully created our first finite state machine and is mimicking the manual approach. Excellent. Our FSM is working just like the manual approach, but automated via a sequence of states, an FSM. But Verilog FSMs, like many Verilog constructs, can fall prey to latches if one is not careful. How does the toolchain decide that a latch has been inferred or has been generated? Well, there are 3 rules that govern this, and they're typically involved with an always behavioral block. The first one is a variable is assigned in a conditional statement, such as an if or a case. 2, the variable is not assigned in all branches of the conditional statement. And finally, 3, the value of the variable needs to be saved between multiple invocations of that always behavioral block. All 3 conditions must be satisfied before a variable is inferred as a latch. Let's return to our module and compare the rules against our code. Here we are in our Mealy state machine, and we are going to focus on the always combinatorial section. More specifically, we're going to focus on the memory address reset. So let's take a look at the rules. Rule number 1 says a variable is assigned in a conditional statement. In our case, it literally is a case statement. It is being assigned. So rule number 1 is true. 2, a variable is not assigned in all branches of the conditional statement. That is also true because in vector 2, vector 3, and vector 4, we don't make an assignment to that variable. Number 3 says the value of the variable needs to be saved between multiple invocations of the always statement. And that is true because in any of the other states, the inference tool is going to assume that we need to store this state for the next invocation. So let's run the synthesis tool, and I will bring that up here, and we will search, and sure enough, in section 3.337, we have a latch that's been inferred, which isn't good. We want to get rid of this inferred latch. So let's go ahead and modify the code. So I'll bring the code back up and put this line in there. This particular line is saving us from having to copy the address reset variable into every state. And you'll find this kind of a structure in most Verilog code. So let's save that, rerun the synthesis. Let me bring this back up. We'll reload section 3.7. And sure enough, we no longer have any latches inferred. So this is one way to deal with latches based on the rule set. But there is another way to deal with latches, and that is to utilize the toolchain's inference capabilities, much like we did with the memory inference for BRAM. I can't honestly say this is a good way to do this, but the toolchain will do it. So let's go back to our code and make sure this line is commented out so that it generates latches. And we'll come back over here. We've rerun the tool, and we can see that a latch was inferred. And if we come over here, we can see that there is a number at the end of this. We'll take this number, 495. We'll go ahead and search for that. And sure enough, down here in section 310.6, we can see that there is this other pass that's going on. And what this is doing is it's actually seeing that a latch can be converted or flattened into a flip-flop. And so at the end of this, when you go to do the routing, the router will not fail because it doesn't see any latches. This was added somewhere in the last few thousand patch updates where they've made the toolchain smarter at dealing with very common patterns when it comes to latch generation. And in this case, Mealy and More machines are kind of obvious. Again, I don't really recommend you doing this. I personally recommend that you explicitly go through and correct your code. We'll go back to the code and fix the latches from even being generated and replaced through inference with a flip-flop. Now we have enough knowledge to build an actual control matrix for our A09, which means in the next episode we will see the actual CPU diagram. There we see every component that we built up to this point connected in some way to completely describe a basic yet fully functional softcore CPU. So stay tuned. Until next time.